Have you ever noticed something? The more you learn about a topic, the less you feel like you really understand. You start peeling back these layers and you think you're getting closer to this core idea, but then there's another layer and another. That feeling of endlessly chasing deeper insights is kind of what we try to do here. We take some super cool source material and we really try to dig in, get to the heart of the ideas without getting bogged down in all the jargon.
Yeah, yeah. Think of it as this curated expedition into complex topics where your guides through these dense intellectual ideas point out some pretty cool views along the way.
Today's expedition. Well, today we're diving into formal epistemology. Yeah, that might sound a bit intimidating, but trust me, it's actually pretty fascinating stuff. And we're going in armed with the always amazing Stanford Encyclopedia of Philosophy. Whether you're already a bit familiar with epistemology or this is your first foray into it, our goal today is pretty simple. We're going to figure out just what formal epistemology is, what big questions it grapples with, and the unique tools it uses to get there.
And those tools are kind of what make it formal, right? We're talking about math and logic applied to some of the most fundamental questions about knowledge itself and how we reason. It's a unique approach to doing philosophy, one that sometimes lines up with traditional philosophical thinking and sometimes goes off in its own super interesting directions.
I love it. So we're going to be digging into some pretty mind-bending stuff, like how do you actually confirm a scientific theory? What are the limits of what we can know? And what about the classic problem of induction? Can you justify learning from the past to predict the future? Formal epistemology can even be applied to things like decision theory and even arguments for the existence of God, which you might not expect. So get ready for a pretty stimulating ride. Okay, first things first, what exactly is formal epistemology?
At its heart. Well, formal epistemology is the investigation of knowledge and reasoning, but it uses formal tools to do so. And by formal, we mean those lovely tools from math and logic. Think probability theory, different systems of modal logic, even stuff like computer modeling. It's about bringing that level of precision those tools have to the study of knowledge.
It's like taking the very precise languages of math and logic and using them to try to understand something as seemingly abstract and nuanced as knowledge itself. Pretty cool.
Exactly. It's important to remember that formal epistemology often deals with the same big questions that traditional, so-called informal epistemology has dealt with for centuries. Things like, what is knowledge? How's it different from belief? Or what makes a belief justified? These are core epistemological questions that both approaches tackle, just in different ways.
Right, the classic head scratchers. So where's the dividing line then? What makes people want to use this formal approach?
The difference is in the methods they use. So while traditional epistemology might rely on thought experiments, analyzing concepts and arguments written in, plain language, formal epistemology brings in the rigor and precision of math and logic frameworks. That lets you build these explicit models of how knowledge works. You can prove theorems that can reveal brand new insights or clarify old debates in a way that's often impossible without those tools. And what's even cooler, because these tools are connected to other fields, formal epistemologists often end up exploring areas that aren't usually part of traditional epistemology, things like how decision-making works or the logic of those what-if statements.
I see. Okay. It's like we're upgrading to these really fine-tuned instruments to examine these old philosophical questions. Let's look at an example, shall we? The text jumps into a case study about how scientific theories are confirmed, which feels particularly relevant, wouldn't you say? How does formal epistemology tackle this one?
Yeah, that's a big one for sure. Back in the early 1900s, there was a big push to try to make scientific reasoning really systematic, and they used deductive logic for this, drawing inspiration from how math had been rebuilt using logic. The goal was to figure out the logical structure of how scientific hypotheses get support or confirmation from evidence. It was seen as a way to make science more rigorous and transparent.
Okay, this deductive approach, as you called it. How would that work in practice? Can you give us a concrete example to illustrate it?
Definitely. Let's take a classic scientific idea. All electrons have a negative charge. Using formal logic, we can express this as, for all x, if x is an electron, then x is a negative charge. Right. Now, if we find a specific particle, we'll call it A, and we'll figure out it's an electron. This general statement logically means that A must have a negative charge. That's just basic deduction. The early idea was that if we then did an experiment and saw that A does indeed have a negative charge, that observation would support our initial universal hypothesis. It's like the prediction coming true makes the theory stronger.
It's as though the hypothesis predicts something, and when that prediction is verified, it strengthens our belief in that hypothesis.
Right. This led to the idea of deduction in reverse, where all the observations we make, along with background knowledge, like knowing A is an electron, would support the broader hypothesis, even if it's not a strict logical deduction. There's this thing called Nicod's criterion, which was a famous idea in this framework. It basically said that a general statement like all F's are G's gets confirmation when you find things that are both F and G, as long as you don't find any counterexamples. So if you see a black raven, according to Nicod's criterion, that confirms all ravens are black. It seemed to fit our intuition about how scientific evidence works.
It does seem to make sense at first glance, but I remember something about a paradox with ravens. Something that really messes with this idea. What's the problem there?
You're talking about the infamous raven paradox. Here's the thing. The statement, all ravens are black, is logically the same as saying all non-black things are non-ravens. Now, if we follow Nicod's criterion, just like seeing a black raven confirms the first statement, seeing something that's not black and not a raven like a red apple on your table would confirm the second statement, since they're logically equivalent. But come on, it sounds crazy to say that seeing a red apple somehow makes you more confident that all ravens are black. That's often called indoor ornithology as a kind of joke. It showed a big flaw in this early attempt to explain scientific confirmation using deduction. It challenged that simple idea that confirmation just means finding examples that fit the rule.
I can see why that would be philosophically troubling. So the purely deductive approach had some serious issues. How did formal epistemology adapt to these limitations?
Well, the problems with the deductive approach, especially when you're dealing with hypotheses that are statistical and don't make predictions about individual cases, like 50% of ravens are black, for instance, led to a shift towards using probability theory. The core idea here is that confirmation isn't this all-or-nothing thing. It's more like a matter of degrees. Evidence can make a hypothesis more or less probable. This probabilistic perspective gave people a way to work with the nuances of inductive reasoning, where you don't always get certainty.
Makes sense. So instead of saying a hypothesis is confirmed or not, we talk about how likely it becomes given the evidence. But how exactly does probability theory provide the tools to make this precise?
It all starts with the basic rules, the axioms of probability. There's this function that gives a probability value between 0 and 1 to any statement, a proposition. Statements that are always true, like those tautologies, have a probability of 1, while contradictions have 0. And for statements that can't both be true at the same time, they're mutually exclusive, the probability of them combined, like A or B, is simply the sum of their individual probabilities. These are like the ground rules. Using these rules, we can then define what's called conditional probability. That's the probability of one event happening, given that another event has already happened.
That's like saying if A has already happened, what are the chances of B also happening?
Exactly. And with conditional probability, we can then precisely define something called the degree of confirmation. This measures how much a piece of evidence, let's call it E, confirms a hypothesis, which we'll call H. It's basically the difference between the probability of H given E and the probability of H before we even knew about E. If that difference is positive, we say E confirms H. If it's negative, E disconfirms H. And if it's 0, then E doesn't really tell us anything about H. This gives us a way to measure how strong evidence is.
Okay, so if I see a black raven, that might increase the probability I give to the statement all ravens are black, even if it's just a small increase, right?
That's the idea. And from these basic rules, probability theory lets us figure out a ton of really cool theorems. These theorems describe how probabilities work and how they relate to logic. Like, for example, we have the rule that two contradictory statements can't both be very probable at the same time. There are also rules for how to work out the probability of combined statements, like A and B or A or B, and how probabilities change when we learn new information. These give us a much more powerful framework for understanding how evidence supports or goes against our beliefs.
Now, this leads us to the very famous Bayes' theorem. It seems to come up a lot in philosophy. What makes it so important?
Bayes' theorem is definitely a big deal. It's this elegant mathematical result that connects the conditional probability of a hypothesis, given some evidence, to the initial probability of the hypothesis and how likely that evidence is if the hypothesis is true. It basically gives you this recipe for how to rationally update your beliefs when you get new information. It's so important philosophically because it links together a bunch of intuitions we have about confirmation and how science works into one short equation. It's a formal way to connect what we already believe to how evidence should make us change those beliefs.
Okay, let's break down that significance a bit. How does Bayes' theorem help us understand things like how well a theory explains the evidence, or how important it is for a theory to make new predictions?
Sure. Let's start with what's called theoretical fit. If a hypothesis strongly predicts the evidence, meaning it's very likely we'll see that evidence if the hypothesis is true, then Bayes' theorem tells us that the probability we should assign to the hypothesis goes up when we actually see that evidence. The better the theory fits the data, the more it boosts the probability of the theory. Then there's the idea of novel prediction, which is really cool. If a theory predicts something we wouldn't have expected, meaning the evidence was initially unlikely, and then we see it happen, well, Bayes' theorem shows that this unexpected evidence is really strong support for that theory. The more surprising the evidence, the more it supports the hypothesis that predicted it. And lastly, prior plausibility is really important. The initial probability we give to a hypothesis before any new evidence, well, that directly affects how its probability changes after we see the evidence, according to Bayes' theorem. A hypothesis we thought was more plausible initially is going to get a bigger boost from the same evidence compared to a hypothesis we thought was less likely to begin with.
That really makes it clear how all these different ideas are connected. Now, how does this probabilistic approach, especially using Bayes' theorem, help us solve that Raven paradox we talked about earlier?
Well, the typical way to solve the Raven paradox using probabilities is to say that seeing a non-black, non-Raven, like our red apple, does give a tiny bit of confirmation to the idea that all raisins are black. It's just a ridiculously small amount. The reasoning is that your observation makes it slightly less likely that there's a non-black raven out there among all the non-black things in the world. There's even a theorem in Bayesian epistemology called the Raven theorem that formalizes this under specific conditions. It shows that the probability of all ravens are black does increase a teeny tiny bit when you see a non-black, non-raven, especially if almost all non-black things are not ravens. The paradox comes about because we intuitively expect either no confirmation or maybe even disconfirmation from seeing something like a red apple, but we miss this very subtle but still logically consistent increase in probability.
Interesting. So that red apple is relevant, but just barely. But there are some important details we need to consider, right?
Yes, exactly. The point is that how much confirmation we get, and even whether we get confirmation at all, depends heavily on the specific assumptions we make about the probabilities in the world. There are cases, like one called Good's counterexample, where seeing a black raven can actually lower the probability of all ravens are black if we have some very particular and maybe unusual background beliefs. Like imagine we start off thinking that the only reason all raisins might be black is because there are very few raisins in existence. Finding a raven, even if it's black, might make you think there are more ravens than you initially thought, which would then make it less likely that they're all black. This shows us something really important. Any claims about confirmation depend on these underlying assumptions about probabilities, and those assumptions themselves need to be justified somehow.
And that takes us right back to the problem of the priors, doesn't it? How do we even figure out those initial probabilities?
Yeah, exactly. The axioms of probability, the basic rules, are pretty minimal. They tell us the basic things any probability function has to follow, like having values between 0 and 1, a probability of 1 for things that are always true, and so on. But for most propositions about the world, those rules alone don't tell you what the initial probability, the prior probability, should be. That's the problem of the priors. How do we rationally figure out those starting probabilities before we have any evidence? Do they always come from some previous evidence, which might lead to an infinite chain of reasons? Or are there some basic principles we can use to figure out those initial probabilities from pure reasoning? Formal epistemologists are divided on this. Objectivists think there are additional logical principles, like the principle of indifference, that can help us determine those initial probabilities in a way that's not arbitrary. Subjectivists, on the other hand, argue that there isn't one right way to do this, and different rational agents might start with different probability functions as long as they follow the basic rules of probability.
I see. So the very foundation of this probabilistic approach has its own set of deep and unresolved issues. Okay, on to the next case study. The problem of induction. This is the classic philosophical challenge posed by Hume, right?
Yes, exactly. David Hume was a Scottish philosopher who famously questioned how we justify inductive inferences. That's our ability to take patterns we see and apply them to things we haven't seen yet, to predict the future based on the past. If we've seen the sun rise every morning of our lives, What reason do we really have to think it'll rise again tomorrow? Hume said any justification for this will end up being either circular, using induction to justify induction, or deductive, which won't work because the idea that the future will resemble the past isn't a logical truth. Hume's problem is still a huge challenge for any theory of knowledge.
So can probability theory help us solve this deep problem? Even if we can't deduce with certainty that the future will be like the past, maybe we can at least show it's probably going to be that way.
That was one idea people explored. But it turns out that just having those probability axioms, those basic rules, doesn't guarantee that conclusion. For example, let's say we consider all possible sequences of 10 coin flips to be equally probable. Seeing 9 tails in a row doesn't actually make the 10th flip more likely to be tails. The conditional probability of a 10th tail, given that the previous 9 were tails, is still just 12. The probability axioms themselves don't favor any particular pattern in a series of independent events.
That's super counterintuitive. It really feels like after 9 tails, that 10th tail is almost due to happen. What explains this neutrality, probabilistically speaking?
The important thing to realize is that the probability axioms don't force us to say that all possible sequences of events are equally likely. We can choose different prior probability distributions. For example, a philosopher named Rudolf Carnap suggested a different way to assign prior probabilities, not based on specific sequences of results, but on the overall proportion of a certain outcome, like tails, in a sequence. In Carnap's system, seeing a lot of tails in a row would actually make a future tail more probable. But, this is key, Carnap's way of assigning those prior probabilities isn't the only way that's allowed by the basic rules of probability. This just shows that those rules are neutral when it comes to the problem of induction. Inductive reasoning fits with them, as Carnap showed, but so does being skeptical about induction, which is what we see when we say all sequences are equally likely. You can even imagine ways to assign those prior probabilities that lead to something we might call anti-induction, where the more you see a pattern, the less likely you think it'll continue. What this really highlights is that probability theory by itself doesn't solve Hume's problem. It gives us a framework, but it's up to us to justify choosing one particular way to assign those prior probabilities.
Wow, okay, that's kind of mind-blowing. So probability doesn't magically solve this problem for us. But the text suggests it can at least help us understand the problem better.
That's right. When we frame the problem within this probabilistic system, it becomes clear that Hume's problem is really tied to the problem of the priors. If we could find a good justification for choosing one specific way to assign those prior probabilities, maybe one that favors the continuation of patterns, like Carnap's, then we might be able to tackle Hume's challenge. But, like we've seen, figuring out how to justify those initial probability assignments is the real sticking point.
Which brings us back to the principle of indifference, right? Can you remind us what that principle is and how it plays into our attempts to justify induction?
The principle of indifference is a pretty straightforward idea, and it seems intuitive at first. It says that if we have a bunch of possibilities that are mutually exclusive and cover all the options, and we have no information that favors any one of them, then we should assign them all equal prior probability.
Sounds like common sense.
Like a way to be fair when we don't know anything specific.
It makes sense. I don't know anything about the people in a lottery. It seems reasonable to assume they all have the same chance of winning.
That's the basic intuition. But as nice as it sounds, the principle of indifference runs into some big problems. There's this classic example with a horse named Athena. Let's say Athena's in a race, and she could either win or lose. If we don't know anything else, the principle of indifference says we should give her a 12 probability of winning. But now, imagine there are 3 horses in the race: Athena, Beatrice, and Cecil. The principle of indifference now says they each have a 13 chance of winning, which contradicts what we said earlier about Athena, because that meant she had a 23 chance of not winning. The problem is that you can often divide up the possibilities in many different ways, and they all seem equally valid. So, for example, Athena not winning could be subdivided into Beatrice winning or Cecil winning. The probability we end up with seems to depend on how we choose to describe or divide up those possible outcomes.
It's like the probabilities aren't inherent to the situation itself. They just depend on how we decide to categorize the possibilities.
Exactly. And this problem gets even worse when you have continuous possibilities, like in Bertrand's paradox, which involves a randomly chosen iron cube. Depending on whether you describe the possible sizes of the cube using its edge length or its volume, which are related mathematically but not the same, the principle of indifference will give you different probabilities for the same event. Like the probability of the cube having an edge length within a certain range will be different, depending on how you describe it. This ambiguity really undermines the idea that the principle of indifference is a reliable way to determine prior probabilities when we're ignorant. And remember how we talked about the coin toss example. Different ways of applying this principle can lead to totally different conclusions about induction itself. If you apply it to sequences of outcomes, you might end up skeptical about induction. If you apply it to general hypotheses, you might be more open to induction.
So, even though it seemed promising at first, the principle of indifference has its own deep problems, and it doesn't provide a clear-cut solution to the problem of induction. I guess this strengthens the split between subjectivists and objectivists about prior probabilities, doesn't it?
Absolutely. Subjectivists look at these problems with the principle of indifference and say, well, any initial assignment of probabilities that follows the basic rules of probability is a legitimate starting point. So from their perspective, you could start with a Carnap-like inductive prior or a more Humean skeptical prior. Both are okay as long as they're probabilistically coherent. Objectivists, on the other hand, are still hoping to find some non-arbitrary way to determine those initial probabilities. They often try to refine the principle of indifference or come up with new logical or epistemic principles. This is still a lively debate in formal epistemology. People are still trying to justify those basic axioms of probability and principles like the principle of indifference, sometimes by talking about how these rules lead to true beliefs.
Okay, even if we could agree on how to assign prior probabilities, the text reminds us that that's just one piece of the puzzle. We also need to figure out how to update those probabilities when we see new evidence. That's where this section on updating an inference comes in.
You got it. Figuring out those initial probabilities, even if they favor induction, like Carnap's, doesn't automatically mean that our new probability after seeing evidence should just be the conditional probability we get from our prior.
Let me put it this way. Suppose you initially believe that if A is true, then B is probably true. Then you find out that A is actually true. You could, based on conditional probability, conclude that B is probably true now, right? But you could also change your mind about how strong that connection between A and B really is. Maybe seeing A and then not seeing B, or vice versa, makes you think your initial conditional probability was wrong.
So just because I've seen 9 tails and I tend to think a 10th tail is likely, doesn't automatically mean my updated belief about the 10th cause should just reflect that prior likelihood. I might, for instance, begin to suspect the coin is biased. Exactly. We need some rule that tells us how to go from our prior probabilities to our posterior probabilities in light of new evidence. Conditionalization is one of those rules. It says that when you learn something for sure, let's call it E, the new probability you give to any hypothesis H should be equal to the conditional probability of H given E that you had before. It's like keeping the connections that were encoded in your prior probabilities. The way you thought things were connected before you had the evidence should determine your beliefs after you get the evidence.
It's like saying, I had this idea about how likely different hypotheses were if this evidence turned out to be true. Now that I know the evidence is true, that should be how confident I am in those hypotheses.
You got it. And there are good arguments for why conditionalization is the right way to update beliefs, many of them similar to the arguments for the probability axioms themselves. They often involve the idea that conditionalization helps us avoid guaranteed losses in betting situations, what are called Dutch book arguments, or that conditionalization leads to more accurate beliefs. The takeaway is that inductive reasoning isn't just about setting those initial probabilities. It's a process where our beliefs change over time as we learn new things. That process likely needs dynamic principles like conditionalization on top of those initial probability assignments.
Formal epistemology gives us a sophisticated way to describe how inductive reasoning could work, but it doesn't magically get rid of Hume's problem. Instead, it seems to push the challenge back to justifying those underlying assumptions. The validity of the probability axioms, how we choose those prior probabilities, and the principles for updating them when we see new evidence. Okay, let's move on to our third case study, the regress problem. This sounds like another really foundational issue in epistemology.
Oh, absolutely. The problem of induction asks how we justify making predictions about things we haven't observed based on things we have. The regress problem goes even deeper. It asks about the ultimate justification for any of our beliefs that are based on reasons or evidence. If we say we know something, we need a good reason for believing it, right? But then what's the reason for that reason? And so on, maybe leading to an endless chain of reasons. Where does this chain end, and how can we be sure it ends in a way that actually justifies our beliefs?
It's that constant question, why? Why do you believe that? Because of this. Okay, but why do you believe that? Because of something else, and on and on. Does this chain of reasons ever reach a solid foundation we can be sure of?
Precisely. The Agrippan trilemma is this ancient idea that lays out the 3 basic ways this chain of justification could end. First, it could go on forever, infinite regress. Second, it could loop back on itself, with beliefs ultimately justifying themselves, circularity. Or third, it could stop at some point with beliefs that we just accept as true without any further justification, unjustified premises. Each of these possibilities has a classic philosophical response: infinitism, coherentism, and foundationalism. And each of these views has its own set of problems that philosophers have pointed out over the years.
Yeah, it's hard to imagine how we, with our limited brains and finite lifespans, could handle an infinite chain of reasons. Coherentism has that immediate problem of circularity. Can a belief really be justified just because it fits in with other beliefs in the same system? And then with foundationalism, we're left with these basic beliefs that are just asserted without any reasons, which feels really unsatisfying.
You're exactly right. Those are the classic objections to each of these views. Formal epistemology has started to engage with these issues, using formal tools like probability theory to analyze coherentism and foundationalism in more detail. The text focuses on these two.
Let's start with coherentism. How does formal epistemology approach this idea that beliefs are justified if they fit together in a consistent system?
The big worry with coherentism, as you mentioned, is that it seems circular. How can a belief be justified by other beliefs in the same system when those other beliefs themselves might depend on that original belief for their justification? Coherentists argue that justification isn't like a line of reasoning, it's more like a property of the whole network of beliefs. A belief is justified because it fits well with lots of other beliefs that are consistent with each other. But then the question remains, could you have a whole system of beliefs that are internally consistent but just completely wrong about reality? In other words, why should we think coherence is a good guide to truth?
I see. And this is where probability theory enters the picture. People try to use it to formally define what coherence is and see if a more coherent set of beliefs is actually more likely to be true.
Exactly. Some formal epistemologists have tried to model coherence using probabilities and see if having more coherence actually increases the probability that your beliefs are true. 2 philosophers, Peter Klein and Ted Warfield, made a famous argument that sometimes making your beliefs more coherent by adding new beliefs that are consistent can actually lower the overall probability that all of your beliefs are true. Their argument uses this idea that the more independent beliefs you add together, the lower the probability that all of them are true. It's a probabilistic effect people call conjunction costs probability. Another philosopher, Shogenji Shin, argued back by saying we also need to consider the strength of a belief system, how informative it is. He came up with a way to measure coherence using probabilities and said that while increasing coherence might indeed increase probability if the strength stays the same, when we add beliefs to make things more coherent, like the detective building a case, we often also increase the overall strength. This increase in strength might sometimes be more important than the benefits of more coherence when it comes to probability.
So this debate is still ongoing. Is there any agreement in formal epistemology about the best way to measure coherence or how it relates to truth?
Not really, no. Shogenji's specific way of measuring coherence has been criticized, and there are lots of other proposed measures out there. The fundamental question of how coherence and truth relate is still a big one in formal epistemology. There have even been other arguments against coherentism using probabilities, some of which have later been retracted or revised. It shows how powerful these formal tools are for analyzing these classic philosophical ideas.
Okay, so what about foundationalism? How does formal epistemology deal with this idea that some beliefs are just justified on their own without needing support from other beliefs, and that these basic beliefs are the foundation for all our other knowledge?
Foundationalists usually point to certain types of beliefs as examples of these self-justifying beliefs. Common ones are beliefs about our immediate sensory experiences, our perceptions, our memories, or maybe beliefs about how things seem to us. The big question for foundationalists is, how are these supposedly basic beliefs justified if they don't need support from other beliefs? A common strategy is to say that the mental states themselves, like the act of perceiving something red, justify the corresponding belief, I'm seeing red.
But then we run into the Salargian dilemma, right? That seems to be a big problem for this idea.
Exactly. The Salargian dilemma throws foundationalists a curveball. It asks, in order for your experience of seeing red to justify your belief that you are seeing red, do you first need to know that your sense of sight is generally reliable? If the answer is yes, then your supposedly basic belief about seeing red actually depends on another belief about how reliable your senses are, which could lead to a chain of reasons. The other option is to say that you don't need to know your senses are reliable for your experience to justify your belief. But then your belief seems kind of arbitrary. Why should just feeling like you're seeing red without any other reason to trust that feeling be enough to justify the belief that you're actually seeing red?
The text mentions that philosopher Peter White used probability theory to formalize that second part of the dilemma. How does that work?
White's formalization uses probability to show that the probability of a belief about perception being true, given that you've had the corresponding perceptual experience, can't be greater than the prior probability that those kinds of perceptual experiences are generally reliable. This suggests that we need some prior reason to believe our senses are trustworthy before we can say that our specific perceptual experiences strongly justify our beliefs about what we perceive. If we have no reason to trust our senses, then just having a sensory experience doesn't automatically make the matching belief probable.
And wouldn't you know it, the principle of indifference shows up again here.
Yep, it pops up everywhere. If we try to use the principle of indifference to determine how likely it is that our senses are reliable, we might end up with a skeptical view. We could say it's equally likely that our senses are reliable or completely misleading. If we start with that low probability for reliability, then our sensory experiences wouldn't have much power to justify our perceptual beliefs. Subjectivists could argue that we can just assign a high prior probability to the reliability of our senses, but then they'd have to admit that assigning a low prior probability and ending up with skepticism is also okay from a purely probabilistic point of view, which doesn't really give foundationalists the solid grounding they're looking for.
It seems formal epistemology gives us these fancy tools to break down these classic debates about the regress problem, but it doesn't give us any easy answers. It just helps make the challenges clearer. Let's switch gears a bit and move on to the fourth case study, the limits of knowledge. Here, we change our formal toolkit again. Now we're entering the world of modal logic, right?
Right. We're leaving probabilities behind and going into the realm of modal logic to explore what can be known and what might be unknowable. We're talking specifically about a branch of modal logic called epistemic modal logic. Standard modal logic adds these operators to regular propositional logic to represent ideas like necessity and possibility. In epistemic modal logic, we have operators that deal specifically with knowledge and belief. We're focusing on the knowledge operator, which we usually write as K, where K means you know that. So we're basically trying to formally define what knowing means using a logical system. What are the basic rules and axioms that govern this epistemic logic? Well, we start with all the usual axioms and inference rules of propositional logic. Then we add axioms that are specifically about knowledge. One crucial one is the K axiom, which says that if you know that C implies use, and you also know the phi, then you know it's pissed. This is the idea that our knowledge is closed under known logical implications. Then there's the T axiom, which is sometimes called the truth axiom. It says if you know phi, then phi must be true. This is the basic principle that knowledge has to be true. You can't know something that's false. Then we have the necessitation rule, written as NEC, which says that if phi is a logical truth, you can prove it from the axioms of the system, then you know that. This rule is usually restricted to logical truth because we don't want it to imply that we know all true propositions. We also have the standard rule of modus ponens, written as MP.
That necessitation rule is still kind of weird. Does it mean we know every logical truth, even the really complicated ones we've never even thought about?
It's a good question. The necessitation rule only applies to propositions that are already proven as logical truths within the system we're working with. It doesn't magically give us knowledge of every single logical truth out there. It's more like saying that those basic logical principles are knowable in a way, or that they follow directly from the text.